Hello everybody. Welcome to the DeFi Summer Hackathon workshop series. I'm really happy to introduce Everett. He's the CTO of Runtime Verification to talk about how you can formally verify DeFi projects.
Thank you. I hope everyone can see my screen. So as stated, I'm Everett Hildenbrandt. I'm the CTO at Runtime Verification, which is a security auditing and formal verification shop based out of Urbana-Champaign, Illinois. And I'm going to be talking in broad strokes about formal verification for DeFi projects, kind of what that process looks like, and showing a very simple example of that process that you could try yourself at home. So let's get started. So first, I'm just going to be talking about formal verification in broad strokes, and then I'll be talking about kind of mitigating blockchain vulnerabilities, which is one of the goals of using formal verification in the DeFi space. And then I'll go through a simple demo just of a safe addition function and show you what it looks like to make a specification and try to verify that it actually is met by the code. So just who are we? We're Runtime Verification. We're a startup, although I don't know if we qualify that much as a startup anymore. We're kind of getting larger. And we use formal methods to perform security audits for a lot of the different blockchain ecosystems. So, we started out in Ethereum in about 2018 and have been expanding to other ecosystems as well. So we've done audits and verification for folks in the Algorand space and the Tezos space. So folks who use Wasm like Polkadot and Elrond, and then also some other blockchains as well. Our kind of mission is to make the software quality assurance tools that we use, the formal methods tools that we use, widely available and easy to use for folks, for normal devs, basically, because historically it's been really hard to use verification tools. And I'm not going to claim we've accomplished that mission yet, but we're certainly getting closer and we're trying to improve every day. So what is formal verification? So formal verification is where you take a piece of code or you take a system, it could be like the design of a train system or something like that, and try to show that it doesn't have any bugs, roughly, quote unquote. So the thing about systems is they can have bugs in all sorts of places, right? So they can have bugs in the design. You could have a poorly designed system. So you're designing like a train rail system or something like that, and you don't account for in the design that you don't want two trains going the opposite way on the same track. So it could be that your implementation, you actually go and build your rail system, and it meets your design, but your design still allows trains to hit each other. So there could be a bug in your design. There could be a bug in your implementation. So you design everything fine about your train rail system, but one of the switch houses that goes to redirect trains onto the correct rails, stuff like that, actually malfunctions or something like that. So that would be like a bug in the implementation of your train rail system. And it's pretty similar for the design and implementation of code systems, which is what blockchain systems are. So you could have some economic model you want to implement, something like, I want to make a stable coin, and the design of your stable coin is not economically sound, for instance, right? So it doesn't actually create a stable coin. So even though your code actually implements your design, your design doesn't actually implement a stable coin. It implements maybe some inflationary thing or something where the coin price oscillates, something other than a stable coin. Or you could have a good design for your economic system, but you implement the code poorly, or you make a mistake in the code, a typo, anything like that, and then your code doesn't meet your design, right? So formal verification can deal with both these aspects: the design, the correctness of the design itself. Does my system actually implement a proper stablecoin? But it also can deal with making sure that your code doesn't have bugs that make it so it doesn't meet the design. And if you do both of these things, if you make sure that your design is sound and you make sure that your code meets your design, then you have a very secure system at that point, right? But they're both different processes with different expertise involved, and it takes quite a bit of time to be able to do both those things. So here's a little infographic about different use cases. The two use cases we have here are the ones that we've been involved in at Runtime Verification. It used to be, prior to 2018, we were working primarily in embedded systems, mostly in automotive and aerospace, a little bit in robotics and automation. And we were building small tools that other companies would incorporate into their overall quality assurance pipeline. So you have a company like Toyota or something that has their own internal quality assurance pipeline, and they would come to us and ask us, okay, can you build us a small tool that we can put in at this part of the quality assurance pipeline that just checks for X, Y, or Z, just checks for these types of bugs. So we'd say, sure, okay, we can build that for you. In the blockchain space, our clients have been a little bit different in form. Most of the projects we work with don't have their own internal quality assurance department. Instead, they outsource all of that to us. One second. Okay, thank you. So yeah, we've been mostly working with a lot of different parts of the blockchain systems, which could be a layer 1 system, a layer 2 system, or smart contracts, token economics, DeFi systems. So most of what we're working with is smart contracts and DeFi systems, where you have some DeFi product you want to release, and it has some sort of front end where users can deposit collateral or something and take out loans, whatever it is. And the back end system of smart contracts is kind of doing the accounting and making sure that the system stays stable. And usually we focus on that back end of smart contracts to make sure it does stay stable and implements what the client actually wants. So vulnerabilities come from either the design or the code itself. And vulnerabilities are very attractive, for hackers because of all the money that's locked up. And usually they're pretty easy to find if you look hard enough. So, here I've highlighted, we focus on design vulnerabilities and code vulnerabilities, things that like social engineering or legal pressure or phishing, or if someone comes to you with a rubber hose and says, give me your passwords, then we're not worried about that, but we are worried about the actual, the code and the design itself. So that's usually what we're working with is first we do a review of your design, and then we do a review of your code to make sure it meets your design. And I've kind of already gone over this, but once again, design vulnerabilities, they're flaws in the business logic, and code vulnerabilities are where your code itself doesn't implement the business logic as intended. It implements something else. That can be as simple as, I meant to type a plus and I typed a minus. Okay, well that changes the behavior of your smart contracts, right? Or, you didn't use safe math when you should have used safe math or something. That also changes the behavior of your smart contract. So that'll be the example I'm going through a little bit later in the demo. So the techniques for mitigating these vulnerabilities, there's a whole spectrum of them. It's not like there's one silver bullet for doing all of it, because ideally you'd be using formal verification for every aspect of your whole design and your code, but formal verification is very expensive. It's very time intensive, both for human time and compute time. So you have to have some beefy machines usually, and you also have to have someone kind of just dedicated to doing that, which is actually usually the larger cost. So, but to mitigate design vulnerabilities, the simplest thing you could do is make a specification. So you just make a human readable, so that'll be in whatever language you prefer. English is a common choice. Just a very thorough description of, if this happens, then I expect that this should happen, and this should happen, and this should happen. Or these three events always happen in this order, right? So you just try to specify all the different behaviors that your system can have on paper first, and that can actually end up clarifying a lot of misconceptions in your head about how the system is supposed to work, because once you get it down on paper, you realize, actually, between section A, where I'm describing widget 1 and section B where I'm describing widget 2, somehow there's an incompatibility between what they expect. The second option would be an audit, which is where a third party is going to review that design specification. And almost every audit, if it's worth much, will produce by the end of it a rigorous specification like I'm talking about in this first bullet point. So actually, if you approach the auditing companies and you already have a specification written, you're making their jobs a lot easier in terms of how much time they have to spend making that specification for you. So that's a really good idea, is to make that specification first, then go to the auditor with the specification and say, hey, here's our specification and here's our code. What can you do for us? And then another option for design is you can make a model of your system, right? So in the example of the train or something, I'd make a model or a computer simulation of the whole train system, and I would just run it. I would say, okay, send a train down this track in the simulation, send one down this track, and I would just see if I just do normal everyday operations on the system, do any trains crash, right? So computer modeling is a huge, a great way to find potential issues with your design itself. And then the final, most, the gold standard is you can do verification. And this is basically where you make a model like we did in the previous one, but you ask it, okay, I want you to exhaustively check all possibilities of the model. And you can do this either by enumerating all the possibilities if it's a finite number, but usually that's not very feasible. So usually you have to incorporate some sort of symbolic modeling where you say, like, instead of saying I have 3 trains on the track, what if I have an arbitrary number n trains on the track or something like that, right? So that's where you would basically be, quote unquote, doing enough simulation, either by exhaustively enumerating or by doing something symbolic, that you've convinced yourself you've explored all possible behaviors of this model. It's kind of a similar story with code vulnerabilities. A lot of the same techniques transfer over, but because of the nature of code versus designs, some techniques are different. So testing, for example, is something that you can do with code vulnerabilities that is a little harder to do with designs. Now, you can do that with designs by making a model and then testing your model, but we can just test code directly by writing unit tests, regression tests, all the normal testing stuff. So that's a great first step. If you don't have tests, it's not worth contacting an auditor, for example. You need to write tests first, just to convince yourself that, hey, on these few specific examples, at least we know it's behaving correctly. And finally, but another option is to contact an auditor, and their auditor will just go through and they'll use a few tools. They'll use a checklist of things they know to check for. They have a fresh pair of eyes. They haven't been staring at the code as long as you have, so it's easier for them to catch just real obvious typos and stuff that your eyes will kind of just glance over. And also logical errors, rounding errors, stuff like that. Lots of little things that all have to be exactly correct. And every little incorrect thing could cause a potential vulnerability. So you have the auditor kind of scan through and check, okay, that's okay. They have a big checklist they go through. Another option is analysis tools. This would be where you're using a computer to do an audit, basically. There's broadly 2 categories, the static analysis tools and dynamic analysis tools, and there's lots of these available. So it's good for you to become familiar with a couple of these. I know Trail of Bits puts out a couple, we put out a couple, Consensus puts out a couple. So you can use these tools, and they'll just catch the most basic of errors. Things like you didn't use safe math here and you probably should, and stuff like that. And so that's a really another good tool to use before you approach an auditor. And then once again, the gold standard is verification. And verification is, in this context with the code vulnerabilities, is you would make a model of your design over here on the left, and then you would be verifying that your code actually has exactly the behavior that your model specifies. So you ask the computer to check every behavior your code could have and make sure that it's a behavior that your original model said was allowed, basically. And that's kind of our bread and butter at Runtime Verification. That's what we strive to produce for our clients as much as possible. It's not always possible given the time frames they have, but that's kind of what we're trying to provide. So how do you do formal verification? Well, I was talking about this modeling thing on the left, this model. That actually serves as a specification of the system. But it's a computer readable specification, but it's a specification. So we'll almost, if we're doing verification, we'll start off with a human readable specification and then turn that into a computer readable specification and then use that computer readable specification to verify the code. So what you need to do formal verification, you need the code you want to verify, which is like Solidity source code. And you need a specification of the code. So what should the code do? That's what the model that I've been talking about is. Let's see. And there's a bunch of ways to write a specification. The first one, like I said, is just in natural language. So you maybe write a white paper, right? Something that just describes, like, I expect the system to do this and this and this, and this is the goal of the system, and here's how I expect it to work. And you write all that down in English or something. And then another option is to use a mathematical formalism. So this is the approach we take. We use K, but you can also use Coq or Isabel or F star or ACT. And I'll be showing off an ACT example later today. But yeah, you need to have a specification which describes the right behavior of the whole smart contract system. And then what do? Well, you feed both the code and the specification into the computer, or you do it by hand. You can also do it by hand, and ask it, check for me that there's no behaviors the code has that aren't allowed by the specification, basically. So the tool might come back and it might say, actually, if I input 3 for X and I input 7 for Y, there's a way for Alice to transfer 7 ether that don't belong to her, and that's not allowed by your specification, right? Okay, so you look at your code and you see, okay, there actually is a way for Alice to transfer the 7 ether to Bobby, and it's not intended by the specification. So either there's a problem with your specification and you need to update it to say that that is allowed, or maybe that could be the case. It could be, oh, actually, I want that to happen. I want it to be that Alice can transfer the 7 ether to Bobby. Or you need to look at your code and see why it is that that's allowed to happen when your specification says it shouldn't. So that's kind of the approach there. And this can be done by hand or using a tool. A lot of people forget that formal verification or doing mathematical proofs is something that people have been doing by hand forever. So you can do this by hand, where you reason through every line of code very rigorously and write down on paper, okay, this line had an addition and this line had a subtraction and this line did a bit shift and stuff like that. And you reason through all that very rigorously. And the end result is you have something on paper that is an argument for why your code is correct. Okay. So I'm going to get into this demo. And looking at the time, it looks like we'll be ending early, but maybe that gives us time for questions and stuff, so that'll be okay. And I can take you through some other examples online. And also let me check if there's any questions. How did you say I check for questions?
Usually in event chat, but more commonly we just unmute at the end with the Q&A. I don't think there's been any people.
Okay, sounds good. So here's a safe addition contract. There's 2 implementations of it. They're both there's one called add and add bad. Add takes 2 numbers, it adds them, and it checks for overflow. So that's like the safe math add version. And then the add bad just doesn't do the check for overflow. It does the addition and just returns the result without checking for overflow. So this is our code, and we need a specification, right? We need something that describes the correct behavior. A specification language I'm going to use here is ACT. This is a semi-human readable. It gets a little hard for humans to read initially, but it's very computer readable. So we can have the computer actually take this ACT specification and this Solidity code, combine them, and ask, is it the case that every behavior the Solidity code has falls into this ACT specification? I'm going to go over this kind of slowly, but the first line, behavior add of safe add, is just a name. That's just a way of saying, like, okay, we're talking about the safe add contract, and we're talking about a behavior called add. We could have called it whatever we want. And then we tell it what function we're calling. We're calling the add function with 2 symbolic values, x and y. So we're going to be asking it to check for any value that's a uint 256x and any value that's a uint 256y. Is this specification met? And then we're adding a precondition to this where we're saying if and only if x plus y is in the range of a uint 256. So what that is saying is, we only expect this contract to behave correctly if x plus y is in the range of a uint 256. That's one side of the if and only if. The other side of the if and only if is x plus y being in the range uint 256 or not being in the range uint 256, we expect the contract to revert, right? So that's a key component here of what this line here says. This if and only if in range uint 256 says if x plus y remains in the range uint 256, we expect the contract to return the addition and not have an overflow. But if it doesn't remain in that range, we expect the contract to revert, right? There's nothing else it's allowed to do. It's only allowed to revert. And that's key because that's actually what's going to fail about our add bad example is it's going to have an overflow, but it's not going to revert afterwards, which is the bad part of the add bad. This next part, the if and only if vcall value is equal to 0, that's just making sure that our add function will not receive funds. You can't send funds to our add function, and store the funds in the contract that the add function is implemented in. So you can't accidentally send funds to the safe add contract, basically. It's not super important. And then we also say returns x plus y. So we're returning the result of the addition only if, the addition doesn't overflow, right? So let me switch screens here. Okay, can you guys see my terminal okay?
Yes.
Okay. Yeah, sorry, it's a mess. Let me clean it up a bit. That pre-demo jitters where you are just running through it about 40 times in a row to make sure it's working, and of course it's going to fail during the demo, but that's life. Okay, where's my safe add? Okay, so here's our safe add contract again. Once again, we have the add function here, we have the add bad function here, and down here we have the act specification, which says that in the case that we're calling the add function, which is the one that does the correct overflow check, we expect in one case if they're in the range, we return x plus y, no revert happens, and in the other case, if we're not in the range, we revert, right? So I'm using a tool called KLab. I'll spell that here, KLab, which you can find at HTTPS. You can find the version I'm using on the MakerDAO GitHub, MakerDAO/KLab. And let me pull up my demo script. And basically, I've already gone through and I've built. I'll contact the organizers afterwards and just provide this little script. But this little script is all the instructions you need for building all the dependencies, basically. So you need KLab, which is this MakerDAO KLab, and you build that by just doing npm install. And then you need solc. I'm using version 0.7, which is before they started using safe math by default in solc. 0.8 uses safe math by default, so it would make this example harder to show off. And this is how you build solc. And then you need KVM, which is our formal model of the Ethereum virtual machine that we use for doing verification of Ethereum smart contracts. And these are the instructions for how to build KVM, basically. You'll have to read the readmes of these respective repos in order to get the system dependencies you need. I already have all those installed, and I already went through and built all these things. And then you'll need to get you'll need to use solc that you've built there to get the bin runtime of our safe add contract here. So you would you'd get that bin runtime and you dump it in a certain file. I'll let you read the KLab repo README has instructions on how to actually do all the individual steps. This is supposed to be more a little kind of high level, so I'll let you read to find out what those individual steps are. But they roughly correspond to, you have to get that bin runtime and dump it in the correct file, which is at, in my case, example config.json. And basically everything in this file stays the same every time except for this implementation section where you put your bin runtimes of your various contracts. So you have to set that up yourself manually every time. We could probably automate that, but just haven't had the need to yet. And then you build the act. So this build act step actually makes it possible to turn this act specification into a low-level case specification. I'll show you in a bit why you don't want to write the case specifications yourself manually, because they're very verbose and it's easy to mess up, basically. So we're relying on the act KLab tool to build them for us without introducing errors. And then you can use the make system that KLab dumps out in order to prove the individual specifications. So that's what we'll be doing here, is using that make system. So I'm just commenting out all the steps that I've already done, which is like build KLab, build SolC, build KVM, get the bin runtimes, build the acts, and then these are what I'm going to do, is run the proofs, basically. So each proof, like I said, has two different cases, right? The one case is all the preconditions are met. So in this case, this precondition, if and only if in range uint 256 is met, and it correctly returns x plus y without overflow. And then the second case is the preconditions are not met and it needs to revert. And so there's two specifications built: safe add pass rough, which is the one where the preconditions are met and we return the correct value, and then there's safe add fail rough, where the preconditions are exactly not met and we revert. And that's what we'll be proving, is that we revert correctly. So I'm just going to go ahead and run this demo script. And you can see here on the right, it is running the, it first built the safe add pass rough spec, right? And it dumps it to a K file, which I'll pull up now, if I can remember where it's stored. Usually you're not looking at these K files directly unless there's something really going wrong. But it's a huge file, so it's not very fun to read. But this is all auto-generated from just that act code, basically. And we can see here, okay, here is that precondition where we're saying that x plus y is in the range of a uint 256, right? So this is how you say it to K directly. That's how you, instead of an act. And then we're also saying, okay, we're calling the add function. So we're telling it, okay, we want to call the add function on arguments x and y, basically. And they're called ABIX and ABIY here, instead of just x and y, right? So, and then we're also saying, okay, the program that we're executing is safe add, right? So I don't expect you to be able to read this. I hardly can read it, honestly. And here's the output. The return is buff32 of a x plus a y. So that's the returns clause of the act specification. So if you kind of poke through it, you can see how each different component here gets mapped to a component here in this larger specification that K can read. So KLab is just a tool that takes these act, much more readable specifications and turns it into something that K itself can read, which is what we use for doing verification. Okay, so over here, it looks like it accepted one proof. So that was the pass proof. Right. Oh, it accepted two proofs, actually. We have the safe add pass rough proof, which it accepted. So that's where it's starting. And then down here it says accepted somewhere. Let me find it. Yep, it says accepted. Okay, that's good. It says, okay, yeah, what I accepted was the safe add pass rough proof. And now it's going to do this safe add fail rough proof. So we could look at that specification too. Actually, I'll pull that up to show you what the difference is at the K level. If my brain would work. It's too hot for brains right now. I think right now it's like 32 C where I'm at. Okay, so here let me pull up the other one. So this was the pass proof where we're saying the preconditions are met. The one on the top is the pass proof where we're saying the preconditions are met. And notice that in the output cell, we have the return value of x plus y, and the status code, we have EVMC success, which indicates that it returns successfully. Here, we're saying, okay, we don't actually care about the output cell. That's what this question mark is. This is where it fails. The precondition is not met. And the end status code that we get is a failure status code. So that would be either that'd be anything except EVMC success, basically. So that could be an out of gas, or it could be a revert, or an invalid, or something like that, right? And we can say, actually, in the case specification of the pass proof, we have these two, which are in the preconditions. We say x plus y is in the range of a uint 256, and v call value is equal to 0. And down here we have exactly the negation of those two conditions, right? We just put a not bool in front of those ands, basically. And that's saying, okay, in the case where it's exactly the negation, we expect it always to revert, basically. That's what we're saying. Let me pull that act back up again to convince you that I'm not lying. So here's the one precondition. It's written a little nicer here, right? And then here's the second precondition. And both of those are exactly negated, basically, here. Okay, so it accepted the first proof, it accepted the second proof, I think. And then I actually asked it to do a third proof that will let us kind of explore the proof interactively. So that's proof accept. And what we have here is the symbolic execution of the safe add in the bottom right. You see safe add fail rough. So it's actually dumped enough information from the prover that we can step through the execution one opcode at a time and see what the EVM state is at any given time. So here I'm stepping, okay, it pushes 8.0, push 4.0. It stores that on the, let me see if I can, here's the local memory of the EVM machine. Stores that on the local memory. Pushes the vcal value, duplicates it, checks that it's 0, jumps, and then here we have a jump instruction. So that's a branch in the execution. So you see in the top we have behavior, and it's telling you have to pick the 0 or the 1 branch, right? So I picked the 0 branch. The 1 branch is less interesting because it just jumps to the end of execution. It says, okay, we go straight to revert because you're not supposed to send any funds to this contract, which is what that 1 branch corresponds to. So we're saying, okay, we're not sending any funds, and okay, so we're executing. Okay, now we did our call data load, which is where we actually grab the arguments that were passed in, that x and that y, and put them onto the word stack. Let me make this bigger, and you can see here on the right, you have ABI-X right there as the first. It's wrapped up in some other stuff going on here, but you don't have to worry about that. The key part is, okay, we have ABI-X in the 0 slot on the memory. And we shift it right, and now it is just the ABI-X. So we're doing some more manipulations of the stack. Come on, keep going. There's our ABI-X showing up on the stack again. And we can keep going. There's our ABI-Y showing up on the stack. We keep going. And finally, we get down to where we're going to actually eventually add those two up, I hope. Yeah, there we go. Now we've added them and we've chopped it. So we're wrapping it modulo 2 to the 256. We keep going. And that's the end of the proof right there. We've step 849 of 849. So we've successfully calculated the correct value for this addition function. So we can step through this is the fail case. So we've probably successfully reverted. Let me see. Yeah, there we go. Yep, EVMC revert. We reverted by the end because we weren't able to eliminate this chop. So if chop will go away if these are in the correct range, but they're not in the correct range, so it doesn't go away. Okay, so that's the fail case, which means, we correctly reverted when the precondition was not met, right? So let's make a version of the proof that's the bad proof, right? So we'll go to the safe add sol, and we have this add bad function instead. So I'm going to just here tell it, don't call the add function, call the add bad function, but the same specification, right? So otherwise it's the same specification, but it's just different code. We're just calling this code instead of this code up here. So let me run that. So first it's going to go through and try to prove the positive case, and the positive case actually still goes through, right? In the positive case, if x and y, if the addition of them is in the correct range of a uint 256, then we will correctly return the addition, right? But the negative case where we're saying if it's not in the range we should revert, that's what's not caught by the add bad. It will still return the wrong, it'll instead have a success, it'll say EVMC success, and return the wrong value. And so we need to prove that it actually reverts correctly, which is what's going to fail here. So let me show you what the JK looks like to get that it's easier to write act, as always. My computer's being slow. Hello?
Yeah, we're here.
Okay. Sorry, it looked like my connection died for a second there, but it looks like it's back. Okay. Yeah, so the only difference here is now we're saying in the call data, we're calling the add bad function, but otherwise everything is exactly the same about the generated K. So we're just telling it execute a different chunk of Solidity code, basically. Okay. And notice that the up here, I have to scroll back a ways because when the K-prover fails, it spits out quite a bit of stuff. That the safe add pass rough spec passed, right? So if that's saying that if the precondition holds, we will correctly return x plus y. That's cool. Okay. And now we're running the safe add fail rough, which is saying if the precondition doesn't hold, we need to correctly revert every time, right? And it's providing a counterexample saying, I found a way for you to not revert when you are calling that one. So we'll explore that proof branch here in a second, but that's the one that it says it failed. And so here we're saying, okay, we look at our behavior tree again and we see, okay, behavior 1 there where we're sending some ether to the contract while calling the add function. It actually passes the spec because it ends up reverting anyway, right? Because it should revert in that case. Behavior 0, though, is the one we're interested in. And if we look through, we see in the final state that we've got x plus y as the return value, but still the chop is there, meaning that it's done the modulo 2 to the 256, and it did not revert. It ended with a successful status code. So we didn't get notified that the overflow, that this chop overflow happened, basically. And that's exactly what's failing. So you have to verify both the positive, which is the non-revert case, and the negative case, the revert case, that it reverts correctly. And in this case, that's what's failing, is it does not revert correctly. Yeah, so that's the gist here. I'm gonna switch back to the presentation now.
Can you just
you can just to show. Yeah, go ahead.
You just show that like again. So we're supposed to know based on it saying, like, based on us knowing the behavior of it and it showing success, or is there like an indicator of like, oh, this isn't how it should perform?
Well, so the indicator would be in the output log here for the most part. So notice here it said reject basically instead of accept. That's the key thing that you would look for. It also is a different status code. It's like status code 124 or something instead of status code 0. So you could incorporate it into your CI. So yeah, there's another proof that it rejected basically instead of accepted. And then above that, an example of when it accepts a proof is like here, proof starting. Sorry, I don't know how to make this yellow go away. Yeah, there we go. So it accepted this proof, for example. So you would look through the log for those accepts and rejects in this case. Does that make sense?
Yeah, that makes sense. That's what I'm talking about. Missed that, but yeah.
Yeah, so I want to switch back to the presentation real quick, and then I can take some more questions. Let me see if I can do this. I think this is the first presentation I've ever given in Discord, so I'm a little bit new to it. Okay, so real-world act specifications. Like obviously that was a pretty simple example, but an example of a much larger body of act specifications is this one. This is for multi-collateral DAI, which is the stablecoin on Ethereum. It's a market-based stablecoin, meaning it uses market incentives and debt and lots of other mechanisms to make sure that it stays stable. But this is actually one of the largest smart contract verification projects that I'm aware of, where they did a full formal verification of everything. And so you can see these act specifications for each different behavior, each different function of like the VAT contract. So the multi-collateral DAI, or just DAI smart contract system, has a bunch of different contracts, and the core of it is called the VAT. And there's a bunch of different functions in the VAT. So here we, are declaring what we expect the behavior of those different functions to be, and then that generates those large case specs I was showing you for each different function, and then it asks A to prove that those case specs are actually met by the code, basically. So here's an example of an add function like what we were looking at before, but this one is adding a uint and an int, so it's a little bit different. It looks a little bit weird. On the left-hand side, we have to say like chop instead, to indicate that it's an int instead of a uint. So this ends up generating about 1,011 proofs, and in order for us to be sure that the code is meeting this specification, every one of those proofs has to pass, basically. So it takes a while. It takes a little over a day to run all these proofs on a pretty beefy, like 48-core machine. But that's okay. You can see some of them get really complicated. You have like frob diff 0 dink of VAT. That's a very specific behavior of the VAT. And here it's showing like, okay, there's a bunch of variables we care about, and then this is what the storage of the contract looks like before is on the left-hand side of these arrows, and after on the right-hand side. And there's a bunch of preconditions. In ours, we only had one precondition. Here's a bunch of them. Here's some more preconditions, and then some more preconditions even. And basically it generates, once again, two proofs. One that if all the preconditions are met, then this state update happens correctly and we return success. And if the preconditions are exactly not met, the negation of the preconditions are met, then no state update happens and we revert, right? So we have to verify both sides of every behavior, basically. Otherwise, you're not getting the full story. So anyway, you can look through that on your own time, and you can also read on the KLab. In the KLab repo here, there's that example, a very similar example to the one I showed here is this SafeAd example. And so you can look through and see the specification given here for it. It's the same one we were working with. And it provides instructions in this repo for how to use this. You need to install all the dependencies I went through, like KVM and stuff like that, and you can start kind of playing with it. And the idea here is that when the code is updated, or KVM is updated, or Ethereum has a hard fork change, or whatever, you want to recheck these specifications to make sure your contracts will continue to work, and Maker does do that for their system. So once again, this is code verification, so we're checking that the code meets the design, but this does not check that the design actually implements a stablecoin, for example. So it could be that there's a bug in the design and it doesn't implement a stablecoin. Although I think we've seen quite a bit of evidence at this point that the DAI system does implement a stablecoin, just based on, it's been stable for years. So I just want to emphasize here the idea of producing a specification, right? You have to basically write down the behavior of your contract twice. You have to do it once in Solidity, which is your your code, and then you have to do it again in some other language, right? And a typical choice is English, like I was saying, for just making a human readable document that describes what you want your contract to do. And then the auditors can take that English description and basically do their by hand verification that your code is actually doing that. For this demo, I chose ACT because it's kind of compact and easy to read, and I figured I could get through the demo. But there's plenty of other languages you can choose for writing that second version of your contract that's an abstract specification. And they all have pros and cons, right? So ACT in this case is really great for simple smart contracts, but it wouldn't be so good for something much more complicated, maybe something that has a bunch of loops or something like that. So for example, we usually aren't using ACT for doing our real world verification. But it's good. It's a good place to start to learn because all the same concepts translate to any of the other frameworks you would use. But the best thing to do always, every time, write an English specification of your contract, no matter what. That's going to be helpful to yourself in terms of your own understanding of your system, but it's also going to be helpful to any auditors that you want to review your code for you. And no matter what, I mean, I don't think of any dev shop that would do it differently. If we're going to go do a verification of some project using a computer readable specification, we're going to start with an English specification just to make sure that we agree with the client on the expected behavior anyway. So it's just a much better way to communicate your intended behavior. So like I said, you can write the K directly, and you saw how huge those writing the K directly would have been. That's why we use ACT. But here's a tutorial. I'll share this presentation with the host here. This is a little tutorial I did, just starting from a completely blank file, building a verification framework in K, and then doing some small verifications in that framework, basically. So it's a series of 6 videos. Takes about 2.5 hours to watch it all through, but it's broken up into kind of discrete lessons. So. Okay, last thing, we're hiring, so, send your email over to careers@runtimeverification.com if you are interested. And then we have a couple of, we have like a Twitter. I'm not on Twitter, but we have a Twitter, a website, and we have a Discord, which is monitored, and that's directly into our Slack, so you can ask us questions and stuff like that. So... any questions we should address now, or anything people want to go over again?
I have some questions just in since you brought up kind of the need for like the jobs. I wanted to know like what is kind of the track for becoming a smart contract auditor? Like what would you recommend for a novice coming in who to become a successful smart contract auditor? Like how should he start and get where you're at?
Yeah, that's a hard one because smart contract auditing is hard. Like it's not an easy thing to do. But I guess what I would recommend is first just get good at Solidity, right? Just understand Solidity, but not just Solidity, also EVM itself, because if you're targeting Ethereum, right? Solidity is compiled to EVM, and many of the code vulnerabilities aren't apparent in the Solidity source, but are apparent in the EVM. So if you want to be a serious auditor, you have to be able to read EVM bytecode directly itself and understand what it's doing. And you don't have to like read all the bytecode, but there will be snippets of it that you'll have to spot check basically to make sure the Solidity compiler is not introducing bugs, because it does. A lot of the early bugs that we found in people's smart contracts was actually because the Solidity compiler itself was buggy and was introducing problems. So just get good at programming in the language you want to audit. If you want to do audits for Tezos ecosystem, then that would mean you learn how to program in Michelson and Lego, right? And so Lego is like the Solidity of Tezos, and Michelson is like the EVM of Tezos, right? And if you want to if you want to audit like Algorand contracts, you would learn how to write Clarity, Algo Clarity, and Teal. So Algo Clarity is like the Solidity, and Teal is like the EVM, right? So just first get good at programming, comfortable with the language, right? And then the next thing I would recommend to do is start to read the audit reports of the big auditing firms. most of them are made public after the audit completes if we recommend a launch. So you can go to those projects' websites and read their audit reports. And there's only a handful of firms that are actually doing any formal verification or that really high level of guarantee auditing. And I guess I would recommend reading those auditors' reports. They're a little more in depth usually than the other firms. And the ones I can think of off the top of my head would be us, like Runtime Verification, Trail of Bits, Certora, and CertiK. And I'm sure I'm missing a couple of other good ones to look at. So I would recommend looking at the ones where they do incorporate a little bit of formal verification. So that would be step number 2. And then I guess like you'd want to kind of test your skills, which would mean, take one of those audit reports, take the code they were auditing, prefix, and see if you could find the issues yourself, right? And then see and compare to what the auditors themselves found, right? And it's hard. Like it takes a lot of practice. So, you have to be kind of dedicated.
What's the background of like auditors that you see in the industry? Are they someone like from your science background, or like what is like what is commonly in like industry right now for the experience?
I can't really speak to all the auditing firms, but the ones that I like, the ones I listed, those 4, all of them hire people who have studied formal methods at university, basically. So we have a mix on our staff, but we mostly hire people who've studied formal methods at university, and they don't necessarily study formal methods for blockchain. They studied like formal methods for embedded systems or something else like that. So I guess if you really want to get good at verification and auditing, training yourself in formal methods is the way to go, in my opinion. Because it changes your mindset. It changes the way you think about code. And that's what I think is really important, is that mindset shift.
I also wanted to get a sense of like what kind of DeFi protocols like get your type of audits, and then like what are common mistakes, because you mentioned that like you need to develop a test suite before that. So I was wondering what are kind of common mistakes that DeFi protocols make when they're first seeking audit.
Mm-hmm. Yeah. Well, the common mistakes, like process mistakes, like not developing a test suite and stuff like that, we've kind of ironed out because we just reject those clients. Because we're not. Here, 1 second, actually. Sorry, I thought my dog was running away, but he's not. He's right there. Yeah, the type of clients that we don't take clients that haven't gone through and done their own due diligence anymore, because we have so many clients applying anyway that there's no point in us doing that. So that kind of is taking care of itself as a problem. Sorry, what was the second part of your question? Forget.
I was just saying like kind of common mistakes, or even in the DeFi protocols that you do reject, like what are like what are kind of reasonings for, and or maybe even early on, before maybe when your client base wasn't as big as it is, like what were things that you're saying like, oh come on, like how did they really put this out to the public? So anything like that.
Yeah. Well, let's see. I mean, the most common errors are arithmetic errors, right? So, like, for example, one that gets everyone, right, that people seem to fall into this trap all the time is when they use the division operator. And I know it sounds like really simple, but using the division operator can introduce rounding errors, and those rounding errors can be exploited. So, like, a simple example is we formally verified the version 1 of the Uniswap contract. So now they're, I think, at version 3 at this point, and we haven't had anything to do with version 2 or 3. But version 1, way back in the day, we verified that one. And we found something where they had to do a multiplication and a division in order to calculate the exchange rate between a pair of tokens in a token pool, because it's a distributed exchange contract. And they were doing the multiplication first and then the division second. and that introduced a rounding error where you could manipulate that rounding error to get an arbitrary exchange rate, which is obviously not the desired behavior of a distributed exchange. You want the exchange rate to be fixed at the correct amount, right? So I know it sounds really innocuous, but just a simple thing as like do multiplications before doing divisions, right? Reduces rounding errors and can keep you from having an issue like that. Another common, like there's been several loan-based projects that we've done audits on where they want to provide some mechanism of like negative interest for some reason or another. Turns out negative interest is highly exploitable. I can't think of an exact situation here, but somehow negative interest was allowing people to like pull out way too much of a loan against their collateral and then not pay their collateral back, but the collateral goes under, but they already took out a big loan. So I don't know, something weird like that. But usually it's just really simple arithmetic errors in the code. And then in the design, people have like this grand vision of what they want their DeFi product to do. And so they add in lots and lots of features, and some of those features don't interact well with each other. So I'd highly recommend, like, for a first version deployment, pick out a core set of features that, you know, without every single one of those features is absolutely in order to make your product work, and launch with that. And then later do an upgrade and add more features if you have proven that that core is stable, rather than deciding we're going to try to launch with everything from the start. So there's been a lot of times we've had to recommend to people, you know, hey, your system has like this core here, and then it has a bunch of extra fancy frills on the outside, and those frills actually cause problems. So if you just get rid of those right now, you can launch your core, because they want to launch early, they want to get to the market or whatever. You can launch your core, and that should be okay. And we can spend more time working on the design of the fancy frills on the outside that users will like. So that's another one, is just kind of feature bloat leads to bad interactions between features.
That kind of, like, I know I'm asking a lot of questions, but that kind of, like, I had a kind of question about that. Like, how do you, with DeFi really booming and more functionality and features coming out, like, how do you keep your ear to the streets to keep updated with the latest, like, security vulnerabilities, and like kind of what resources do you use, and like how do you so how does that account like new security vulnerabilities into like current audits? Can you explain like kind of like how you discover stuff like that, or
Well, I don't. Like, I'm pretty much totally disconnected from social media, but we have a couple people on staff who are kind of our social media gurus, and they listen for those things happening. Fortunately, fingers crossed, we haven't had any big exploits of contracts we've audited, but that's, I say that now, and watch tomorrow, there's going to be an announcement like thing audited by Runtime Verification got exploited. But they post them to our internal channel, and then we review them internally, and we see we check, okay, using our current audit process, would we have been able to catch this exploit? And if the answer is no, then we change our audit process slightly. We make sure to add something new into it that would have caught that exploit. So it's kind of an adaptive sort of thing when we see that happen. Does that make sense?
Yeah.
I'm personally not very connected to social media, but we have a couple people on staff who really are, and they always are posting like, oh, look, this thing got hacked, like, could we have caught this? And then we do a real quick analysis to see if our audit process would have caught it, basically.
Yeah, and I see a lot of like, especially for these new protocols, there's specific auditing firms that don't do verification, but that are like the go-to for like yield farms, or like, or even for like ROI contracts. They always go to this specific audit firm. So it's kind of like what is kind of a guide for understanding the legitimacy of an audit, and like what it like. Is there kind of like a diagram for like, okay, what the most valid audit versus like, and then like a chart of companies that do what? That would be very helpful, especially for DeFi protocols that may not be able to afford like a runtime verification audit.
Well, I don't know about the audits that are kind of in the lower tier than us. I know about because we're kind of at the highest tier. of expense and return. But in that tier, I know it's like us and Trail of Bits and CertiK and Certora. I think I'm pronouncing that right, and I'm sure I'm missing some. But I would say that your rule of thumb is how long did they spend auditing the code? Because no matter what, if you spend 2 days auditing the code, you're simply not going to catch as much stuff as if you spend 2 weeks auditing it. And auditing is an ongoing process. It's not like, unless you're able to formally verify everything, and I mean like you make a model of the design, you verify that that's correct, and then you verify that the code actually meets the design. Unless you do that whole entire thing, which I'm not aware of any projects that have done that whole entire thing, then you can't be sure that there's not bugs. So it's just a matter of, we usually pick some core, we formally verify that core, and then we do a manual audit of the rest because it's quicker. And it's just a matter of spending time with the code. Like, you read it, you think about it, you build models, you ask the devs questions like, did you intend for this to happen and that to happen? And so if you see an audit report that only took 2 days to produce, it's probably not a very good audit report. Like our normal quote is, for every 1,000 lines of Solidity code, it takes us 3 weeks. That's kind of I'm skeptical of any audit reports that take any less than that, basically.
Yeah, and that kind of makes me skeptical of my own investment practices, because there's some auditing firms, especially with yield farming, that are super super high ROIs when you get in very early. So they like come up with auditing firms to get the audit on the launch, and then that's kind of taken as a holy grail. Let's ape in, and that's kind of the degen culture that's emerged. So they definitely, based on the number of audits that are putting on their net, they definitely did not spend that much time. So it's making me like, oh wow, I just put my money into a bunch of projects that weren't completely audited. So that's good insight.
Yeah, I mean there's value to, I mean those a lot of auditing firms that have that super fast turnaround, usually they're doing tool-based audits, so they'll just run some static analysis tools and make some code recommendations or something like that. But tool-based analysis is almost never, and I'm not aware of any tools that will extract the design modeling aspect out of it, which I have found that the design modeling aspect of it is actually where the most critical bugs are found. So that, I think, is the important bit, is that you have some human who actually sits down with your devs and says, okay, we're going to really hash out what it is that your design is. We're going to hash it out in English first, and then we're maybe going to make a mathematical or computer model of your design and just make sure that your design works, even before looking at the code. Usually that's how our audits goes. We spend a couple weeks just hashing that design out with the customer, just constant feedback every day. We invite them to our Slack channel, and we just every day are talking to them. And then only once we're all satisfied with the design do we move on to looking at the code. And satisfied with the design here means, from their end, okay, they're convinced that we have a good understanding of their intended design. And from our end, it means, okay, this design doesn't cause any vulnerabilities that could have unintended consequences in terms of, like, okay, someone can come in and extract all the funds, or someone can attack this with flash loans, or someone can, whatever it is that that could be a vulnerability for that one. So I think that if it's a tool-based audit, which most of these fast turnaround audits are, you aren't getting any of that design component, basically.
Yeah, that answers that. I mean, I wrote a list of questions and you just answered them all. So anyone else has any questions?
Actually, so you mentioned that you need to get, I'm just getting into Solidity development, but I think, do you think it's useful just to look at these audits for problems when we're writing our own Solidity code? Because you mentioned that division error, and I was writing something for like a yearn vault. And I remember we were working with compound C tokens. So there was an exchange rate thing. And I think I actually didn't account for that myself. So do you think it's useful to look at some of these audits just for errors in our own Solidity code when we're writing?
Yeah, a good audit report will also tell you its methodology, because a good auditor will never ever make the claim your code is safe. A good auditor will instead say, these are the things we did in order to check the safety of your code, and here are the results, right? And so that is not a claim like your code will always be safe. That is instead a very open and honest communication, like, you know, we checked for X, Y, and Z. We used these techniques to check for X, Y, and Z, and this is what we found, right? And there, you see what the difference is there between saying like your code is safe, which is usually not true. Like it's unless you, like I said, do a full verification of everything, there's no way you can guarantee the code is safe. Instead, you should have a methodology section where you basically say like, we're going to check for these, we're going to check for that, we read through this, we made this design, we checked for reentrancy here, we checked for that there, so that you can read the audit report and figure out that methodology they're using and just use the same methodology yourself, right? Does that make sense?
That's solid. Yeah, that's solid. You can look at the audit report, and if you're seeing their methodology, you can just do it yourself. That sounds good.
Yeah.
I'll start looking at them now then.
Yeah, please do. Like the audit reports that the bigger firms publish are very thorough. They're super well done, and a lot of them have links to like, this is the list of vulnerabilities we checked against. And like I said earlier, when a big hack happens, we look at that hack and we see, is that hack accounted for in our list of things that we check? And if not, we update our list basically.
Okay, yeah, that's solid. Okay, thank you.
Mm-hmm. Anything else, guys?
Yeah, I think that might be it, unless anyone wants to talk. We are going a little bit over time. I really thank you for going into all those details. It really educated me and made me think in a more safer approach to how I look at DeFi projects. So thank you for coming on and answer our questions.
Yeah, I'm always happy to help people understand